to some of the stuff that I'll be talking about. Computational biology is a huge field, and we're not going to touch probably even 15% of it. But some of the ideas from parallelism we're going to talk about. So I'm going to motivate pretty much everything I'll talk today through the genome assembly problem, but they're useful in a lot of other things. In fact, some of the methods are still used for text compression, searching over text by internet companies all over the world. In fact, there's this section in suffix arrays. One of the co-inventors of suffix arrays is now used to be the vice president of Google and responsible for everything related to search. So I guess the data structure has more applications outside biology. So genome assembly problem, you've heard about this quite a lot. It is the puzzle-making situation, right? You're trying to reconstruct a genome. You have sequence data. In this particular case, we'll think about short reads, relatively 100 to 250 base pairs. But know that the technology has been improving, and there's been longer and more error-prone reads that might require different abstractions. The problem is there's a good analogy to this problem from assembling books that are manufactured by different publishers. So they have like different pages. They're shredded and multiple copies of the book. Then you're trying to reconstruct the final book, and you don't know anything about what it is beforehand. So you can form an analogy completely using this book, or you can use it from a puzzle analogy. You have multiple copies of the same puzzle, but essentially they're cut different pieces. Book ones makes more sense because there are multiple publishers for the same book. You're not going to probably find the same puzzle from different companies cut different ways. It's hard because there's no reference, short genome. There are some errors in this particular case. Repetitions are significantly troublesome for this problem. But we're going to focus more on algorithms as opposed to why genome assembly is hard. Also know that human genome is not the biggest genome. It's not the size of your genome that matters. Usually, it's about what you can do with it. So plants have a lot of redundant genomes. They've been carrying it around, copying it. Bacteria, for example, is very efficient. It's going to have very little redundant genome, non-coding genome. Humans are somewhere in the middle. They can afford to copy some redundant pieces, though we might not know whether they're actually redundant or useful. So a sidetrack on biology. So HIPMER is high-performance genome assembler, De Bruijn-based, and it's based on this an earlier serial assembler called Miraculous. So the way HIPMER assembles genomes is it starts from the reads, and it cuts these things into even shorter sequences called k-mers, something like 51, 61, some number like that. And then the k-mer analogy is nice because you can find overlaps of k-1 using these k-mers very efficiently. You don't need to do an expensive overlap calculation. All you need to do is, shift your string by 1 and attach one of the extensions and check the hash table whether it's there. You've done this in homework 3 in a slightly simplified way. The reality is a little bit more complex, and I'll talk about this. And the goal is to assemble contigs. Again, this is homework 3 you've done. What you haven't done is how do you go from reads to k-mers. It looks like chopping something off to smaller pieces should be a very simple problem, but it's simple to state, hard to execute problem. So we'll talk a little bit about how to go to reads to k-mers, and then from contigs to scaffolds, there's a lot of steps. Basically, scaffolds are how do you put contigs together? Like, how do they orient with respect to each other? What's the gap? How deep is the gap? Can I fill this gap somehow by using the information that I already have in the reads? And that, I'm not going to talk all the 11 different modules of HIPMER that do rounds and rounds of scaffolding, but one important piece of it is the alignment. There you will need to align the contigs you just assembled in the step 2 back to the reads, so that you try to see, okay, all these reads are falling in between these two contigs, so I can maybe fill in that gap using that information. And that the expensive part of that operation will be aligning contigs which you have good confidence that to be correct to reads which you don't have that much confidence. Reads can still have errors and all sorts of other things. And there's different computational aspects of this, which is somewhat exciting from a parallel computing and high-performance computing standpoint. Reads to k-mers is really a I/O-bound, high-bandwidth computation and takes a lot of memory. And why is that? Because think about a read of 100 base pairs, and your k is 51. So how many k-mers you will generate from that, if you think about it? This is a sliding window. So the read length minus k is +1, I think, is how many you will need to generate. And if your read length is a little longer, 250, basically from a single read, which is only 250 base pairs, you just generated 250 base pair things. It's significantly larger, even though, even if you find a way to represent these k-mers using only 2 bits, which is what we do efficiently, you're still bloating up the memory temporarily. So to eliminate those, there's quite fancy data structures. The graph traversal and the construction steps were usually latency bound, as you might have observed in your homework. And the last scaffolding step, at least the alignment piece we're going to talk about, is significantly compute bound. So what's happening in the k-mer analysis? So you have the reads, and every processor reads a separate section of the file, and you can do this efficiently with fast parallel I/O, and then they will independently chop it to k-mers. These are all string manipulations. You can implement your fancy string manipulation code or just use STL, depending on your needs of performance. But the more important thing is, at some point, you'll need to count these guys. And there's a lot of these k-mers will be errors. And why is that the case? Imagine there is only one error in your 250 base pair read, and your k is 51. How many, if it's somewhere in the middle, how many wrong k-mers you will see?
51.
51, yeah. So basically, you have one error, which is what is it, 0.4% error rate, one error in 250. But with that, in the end, 1/5 of your k-mers from that, 1/4 of your k-mers from that read will be wrong. So this is how the errors blowed up. And in fact, I'll just move forward and come back. This is what it looks like. So there's a standard single genome in short-read sequencing histogram looks like this on the x-axis. This is the coverage. You basically tried to cover the genome 40 times in this case, and therefore there's a peak on 40. For diploids, there's a little peak farther later there because of the polymorphism, but let's forget about that. And there's a very high frequency of k-mers that occur only once because of these errors. So there's the peak on the left. So they're kind of not important, right? These are errors, and even if they're not errors, it's very little information in there. You can't trust this much data unless you're desperate for it. So what we do is actually, instead of blindly counting these things, we use something called a Bloom filter. A Bloom filter is a probabilistic data structure. It simply answers your set membership queries. Is this data in my set so far? And it doesn't have any false negatives, meaning that if it says, I haven't seen it, I clearly haven't seen it. But if it says, you have seen it, there might be an error, because this is a very compact data structure, and its size is smaller than the cardinality of your input. There'll be some collusions, and I'm not going to go into detail how Bloom filter is implemented, but you can think of it, you can drive this false positive rate as small as you want. There's a trade-off between size and false positive rate. And what's the benefit here? So if I always use a Bloom filter first, instead of blindly counting it, I ask the Bloom filter, have I seen this k-mer before? And then it says, no, you haven't seen it. Well, I will first put it in the Bloom filter and don't start counting it, because I haven't seen it before, right? So it might just be a k-mer that happens only once, and therefore error, and I don't need to bloat my hash table when I do counting. But if I see the k-mer and the Bloom filter says, yes, you have seen this before, then I'll start counting for real. there is a chance that 5%, 1%, whatever you set your error in balloon filters, you might be counting unnecessary things by a little bit, but you will be eliminating a very significant portion, so that saves a lot of memory. So that's a digression, but our parallel K-mer analysis will use balloon filters, but the important trick in parallel is a K-mer, the same K-mer can occur in different processes naturally. It will occur. If the K-mer happens 40 times, it'll happen in many, many different processors. So you can't really use this balloon filter thing independently, because one processor will ask, have I seen this K-mer? And it will say, no, of course. But the other processors have seen it. So how do I serialize this computation and make sure the balloon filter optimization works out? We'll actually do a very dumb thing here. We'll just do an owner counts thing that we've been doing in matrix multiply algorithms as well. So the K-mers are all hashed to a processor. So it's deterministically mapped. Each K-mer is counted by only one processor. So all you need to do is to, do an all-to-all, and the receiver will first create a local balloon filter and ask that local balloon filter, have I seen this K-mer before? And then it can trust it as if it's serial computation. The expensive part of it is this all-to-all communication of K-mers. But, that's fine. And that requires multiple passes. Essentially, 3 passes is implemented in HIPMER for memory efficiency. You can get away with 2 if you're okay with storing K-mers temporarily. But if you're doing a streaming algorithm, you will actually need to do 3 passes. And you will need to do a pass after this to make sure you correct for these 1%, 5%, whatever mistakes the balloon filter made in order to get the count right and eliminate the singletons that pass the balloon filter accidentally. And then there's a step before this where you actually count distinct elements so that you can initialize your balloon filter efficiently. You can eliminate that step and try to use a dynamic balloon filter. They're not particularly efficient. So that's what's basically happening here. This is the second step, initial balloon filter, and that will set your hash tables. And a final step that's awfully similar to this. Only difference is you will correct for those. There's no balloon filters. You will use the hash table you created in pass 2. And plus, instead of just counting, you will also keep track of extensions. So in your homework, you will remember that you got some K-mers that you knew whether they were dead ends or things like that. I think we didn't have forks in this homework. But in general, the way it's characterized is for each K-mer, you count all the nucleotides that happen on the left and on the right. So you basically keep 4 counters for the left extension, 4 counters for the right extension, and then you look. If one of the nucleotides is clearly the winner, then it's uniquely extending that direction. If there is 2 contenders, both of them are above certain threshold, statistically calculated, you say there seems to be some polymorphism, a fork happening in the genome. And then if all the extensions are below some statistical threshold, means it looks like this is a dead end for me. So for dead ends, you put an X, whatever. It's just internal signaling of the code. It's not important. So that's basically your output. Your data will shrink, which is nice, because all the K-mers that happen 40 times will be represented only once. Right? And all the errors will be eliminated. So your data from the reads at the end of K-mer analysis will be smaller at the end. And that helps with the next expensive step. I'm going to skip this thing. This happens when the owner count creates a load balance issue. Because sometimes certain K-mers happen so frequently that whomever needs to count them become heavily burdened. And the way you fix that is, in one of the earlier stages while you're figuring out the cardinality, so using similar statistical algorithms, you can actually figure out which K-mers are so-called heavy hitters, meaning that they occur more frequently than anything else in the data set. And those algorithms are pretty fast, and they require almost no communication. So you can identify these guys super efficiently, and then you will spatially treat them instead of doing owner counts. It helps. So let's come to the graph construction. You have, I think the only difference here from your homework is the reality that you don't know where the beginning of the contig is. I think in your homework there were special k-mers that said this is the beginning of the contig, so you were just walking one direction. In this particular real case, the whole abstraction is the same. I'm not going to repeat it. K-mers are keys in the hash table, and the values of these hash table are the edges that determine what's the next k-mer, right? And this is the implementation you more or less did. And I think you haven't done this optimization, but in practice, what makes this code go fast in the construction step is instead of creating this hash table in a fine-grained access manner, like every time I see a k-mer, I basically insert it. That doesn't work very well in terms of performance because I'm doing remote data puts for every k-mer. So what you want to do is to aggregate all the updates, and then push all of it at once when there's enough of them. That saves a lot of latency and round trips in the network. And this is possible because there's a phasal behavior of this algorithm, right? First you construct the hash table, and then you use the hash table to traverse the De Bruijn graph. Because there's a phasal property, I don't actually need to keep the hash table consistent for every k-mer. It just needs to be eventually consistent at the end of the construction. So I can just buffer updates and just push them in one go. So that's one optimization that's commonly used in all of these operations, so pretty simple. And here's the algorithm. You pick a random k-mer. Now, different from the homework, this k-mer can be in the middle of a contig. So I'm going to start walking to one direction, and then I'll have to walk to the other direction eventually. So I pick the contig, P0, pick this guy up, and then it will start walking to the right, it'll see a dead end, and then it will start walking to the left. Doesn't look that crazy until you see conflicts. So this looks easy, except that what do you do if processor I picks a random k-mer from a contig, but then some other processor also picks it up from the same contig, right? So processors J, I, and T all pick k-mers from the same contig, and this happens for long contigs. You can bound the number of times this will happen using a probabilistic argument and say that the amount of times that you will need to resolve this kind of collisions is rare, but it only follows an assumption that contigs are more or less uniformly distributed. And context lengths are not uniformly distributed. In practice, we see good performance, but what you need to do instead of backing off and saying, processor I should stop all the things that it has done and dump all that data, and same for processor T, and say that processor J is going to finish all of this thing. That requires a lot of redundant work, because all the work that processor I has done so far and processor T has done so far will be wasted. More importantly, if you have a long contig, the whole iteration will be serialized. So instead, there is a slightly sophisticated scheme. You can basically see you basically attach the subcontext your conflicting processors have so far generated to your own, and that can be done in practice. So that saves you not only from doing redundant work, it also eliminates the long contig problem where you would be burdened by the critical path of assembling one contig, whoever is responsible for that. In practice, this works very well, but this is not a talk, so I'm not going to talk about performance results. Then I'm going to go into scaffolding, which is going all outside the De Bruijn graph abstraction. But I want to ask, I maybe did it too fast, so I'm just going to ask you to pause and ask me any questions. The reason I went really fast is because this is a homework. You spent quite a bit of time. not everything I've talked is the homework, but quite a bit of it is. Question?
So with the Bloom filter, for the very first time you see a contig, how do you know it's not false? How do you know it's not an error?
Sorry, not context, but K-mer. So let's forget about parallelism for a second, right? I see a K-mer, and I ask my Bloom filter, do you have it do you have it in your set yet? And the Bloom filter says, no, I haven't seen it. So there's no error there. That side of there's no false negative. If the Bloom filter says it doesn't exist, it doesn't exist. So the only time the error happens is the Bloom filter will say, I have seen this, but in fact it hasn't seen this K-mer. It's just there's a collision from the previous K-mers mapping to the same locations in the Bloom filter. So in that case, imagine what's happening. I am thinking that I have seen this K-mer, therefore it should not be an error, because I'm seeing it for the second time. I insert it on my hash table. So I will get an extra item on my hash table that I'm accidentally counting. But what's going to happen at the end, at the next stage, because I'm doing two passes over the data to correct for this, I'll see that this hash table entry I accidentally inserted from the Bloom filter mistake will only have a count of 1. Then I'll be able to say, look, this just accidentally slipped in because the Bloom filter collision. So they shouldn't be there. Therefore, I'm just going to delete it. The second step deletes anything that has count 1. So that fixes it that way. The whole purpose of the Bloom filter is, if it happens once, do not create a location for it in your hash table. And for some genomes, it saves 5 times, 6 times memory in the hash table. That's all. Other questions? Okay, so we're going to go on parallelizing scaffolding, which is how do you fill in the gaps between contigs and how do you orient them with respect to each other. But in fact, all we're going to really do is teaching something more general, how to index genome data using what's called a seed index table or seed hash tables. There are different names for this. So the goal is you have contigs you trust, we call them targets, and you have reads you don't particularly trust because they haven't been pruned. The contigs you trust because all the errors have been eliminated through K-mer counting and contig generation. So you're trying to find these mappings between reads to contigs so you can fill in the gaps. Great. The way this works, I mean, the trivial way to do this is you would go over all the reads. For each read, you would compare it to every contig, right? Using an expensive alignment algorithm we'll see in 10 minutes. But that's very expensive because you would then be doing, if the cardinality of your read set is R and the number of contigs you have is C, R times C alignments. That's a lot of alignments, and each alignment is not a constant time operation. You'll see each alignment is quadratic on the sizes of the contigs itself, we'll see in a second. So that's not a great idea. Instead, there's a theorem that basically says if two sequences align by pigeonhole principle, which I'm not going to go through, there must be a short subsequence of it where they perfectly align, meaning that there should be a subsequence where this is exactly happening in read 1 or whatever, sequence 1 and sequence 2, if these things are going to align up to certain percentage. And this percentage determines how long the seed can be, but in general, you can prove this by pigeonhole principle. If there is no continuous segment that they both share, they can't be aligning well anyway. So using that argument, what we're going to do is construct a hash table that's awful like the construction in the De Bruijn graph construction phase. We're going to use UPC again, or UPC++, or anything with one-sided memory puts and gets. So I'm basically going over the contigs that I trust. And let's say I chose my K-mer length to be 3. So for each I'm going to slide my window just like in the previous section and create k-mers from my contigs. ACT is my first contig, and I'm going to insert it to somewhere in the hash table. Okay, good. Now I'm going to insert my next tree merge into the hash table and finish it for all the contigs that I have. Now, so far I built my seed index table. Now this is the construction phase, and we have parallelized this as well. Most of the work so far thinks that this step doesn't need to be parallelized, simply because in many applications, for example, human genomics, where there is not a cancer or some highly mutating piece, if you're just aligning your own genome to a known reference, you just need to construct this table only once for the reference, and then that doesn't need to be parallelized that much because I can wait for a day or two. It only needs to be once. But in this context, we're talking about de novo genome assembly. You're basically doing this for each genome from scratch. So therefore, this piece needs to be parallelized, otherwise it will be the bottleneck. So this construction can be parallelized by using remote put operations, simply. Right? Think of this table as distributed for the purposes of parallelism. And now when you need to query this data structure, you're going to do the same thing. Slide window, extract a tree merge, and then, oh, it's not found in the seed index table. Then you try the next one and see how many times it will happen. Right? So in this case, it will happen only once. So this read can potentially align to this contig. That's all it says. I'm not confident that it will align. All I'm saying, there's a chance. Now, after this is found, I'm going to go and run an expensive alignment to see if they actually align to each other and how they align. Like on the edges, or one of them is completely contained in the other one. We'll see how that goes. But this just gives me the candidates. So the whole purpose of this step is to eliminate the R times C pairwise alignment comparison to something much smaller, the linear, ideally, but I can't really give a bound on it. So then I'm going to try. It might be aligning in a location where there's, in this example it's not happening, but it could have been the case that this seed exists in multiple targets, right? Which just basically tells me that my read is potentially aligning to multiple contigs. That's good. I mean, then I'm going to resolve it again by alignment. And in a minute, we'll see what I mean with that. Any questions? So this is kind of fascinating, right? These are very trivial parallel algorithms. All I'm doing is explaining the serial context and then copying out and saying that remote puts, remote atomics will automatically solve this. In fact, for these kind of problems, it does. It's very convenient. But from now on, we'll actually go on to some rather sophisticated algorithms. Sequence alignment. So I said, once you find the candidates, then you have to figure out whether they actually align or just this shared tree merge was just by accident. Right now I need to actually check whether they align. So what are the algorithms for this? The goal here is trying to find the alignment between a sequence where in this picture on the left, I'm represented as in the first column here, to another sequence on the right. And so what is the best way these things align if they ever? It's a dynamic programming algorithm, and the recursion is you decide the cost function. But the nice thing about this computation is if you write down the recursion, you basically see at every step, let's define M to be the score so far, how well these things match, right? The matching score. So there can be three different ways. And I and J are the indices to the sequences. I is the index to the sequence on the column, first column, and J is the index to the sequence on the first row. So I'm moving these things, right? And every time the optimal path can be one of the three ways. It's either there was an insertion in sequence 1 that didn't exist in sequence 2, or there was an insertion in sequence 2 that didn't exist in sequence 1. And those cases are represented on the top two cases, where you just basically look at the score on right above you or right to the left, plus whatever the penalty you put for missing an insertion. I call them the gap penalty. Or it can be that just the sequences -1 in both of them, plus their matching score. If they differ, then there's a penalty. If they agree, there's a bonus. Right? So your matching score keeps increasing as you match. So it's one of those three, and you keep the max. Right? If your gap penalty is smaller than your mismatch penalty, even if both of them disagree, you would keep taking the, for example, the diagonal path versus the other. But you define these gap costs and mismatch cost, and for some applications, one of them make more sense than the other. Okay, so how can I compute this? You can compute this very different ways. Like, you can see that this recursion doesn't depend on a lot of things. Once you make sure that the top left side, which is M00, is 0, then you can now start defining things. Well, the guy next to you is -1, -2. You can fill the first row by minus times whatever the number of nucleotides you've seen in sequence A, and similarly you can fill the first column. Now you fill the first column and the first row. This is the base case. The recursion will take care of itself. You can fill this table either row by row, column by column, diagonal by diagonal. See, as long as the dependencies are satisfied, you can fill this table any way you like, and you will never need to recompute elements by doing dynamic programming. Does anyone not know dynamic programming? For those of you who are watching this and haven't taken a CS algorithms class, whenever you have a recursive problem like we have now, instead of recomputing the previous values over and over again, what dynamic programming allows you to do is to save them and just reuse them. So that's what we're going to be doing. And the complexity of this algorithm finally is MN. It wasn't MN when it was first published, which is kind of strange. But for certain penalty scores, it wasn't trivial to get MN. For certain penalty and gap scores, it was okay. For some of them, you had to do extra tricks and subsequent publications. But right now, everything there is MN. So what's the problem with this idea? I call this finding globally best alignment, meaning that I give you two sequences, and you tell me the score if I force them to align to each other globally. And there's something called the local alignment. And both of these pictures are from Wikipedia. You can actually see it. So this is the dynamically filling the, before that, let me go back. Okay, I filled the table. Now how do I find the best alignment? I mean, the dynamic programming will only give me this table in full. So what do I do after that? Any guesses? It's actually in the picture. So the whole arrow structure is the optimal alignment. You start from the right bottom section, because that's the end of both sequences. And then you either kept pointers for the decisions you have made, this max decision on the recursive formula, or you don't need to keep pointers. You can just recalculate what decision you made by just doing 3 comparisons. Like, how did I come here? How did I come here? You don't need an extra table. And then you will create all the paths. There might be multiple paths, because the maximums might be, there might have been ties. So if there's multiple, you'll output both alignments. Okay? But the trick here is you're starting from the bottom right, because you're trying to find the global alignment for both of them. You can't find subsections of these things and say that, there's an alignment where the middle section of sequence 1 aligns perfectly to the beginning section of sequence 2. Unfortunately, global alignment doesn't solve it. But local alignment does. So that's the famous Smith-Waterman algorithm. And look at the gap, forget about the picture, look at the score. What's the difference here from the previous one? This one is the recursion of Needleman-Wunsch algorithm for global alignment, and this is the recursion for local alignment. Do you see a difference?
Scores are always positive?
Yeah. So there is a fourth option, which is 0, which never lets you become negative. And why does it allow you to find things that are in the middle? Like now what's happening is, in this point in the figure, what? Okay. I didn't know the GIF even went there. So the scores always stay positive. For that reason, the best alignment you can find by looking at the highest score in your matrix and then just follow that path. This allows you to basically pop, the local alignments pop out because you never have accumulated penalty so far. So imagine that between two reads, these are big ones, and there is a really good alignment here in this section diagonal, but it's farther from the global alignment optimal. Since until coming here I already paid the penalty of -4, it's hard for me to recover from -4, so it never actually pops out. By keeping everything positive, you basically are having these local alignments pop out easily. People don't accumulate that. It's kind of good, right? But that's it. There's nothing different there. And then the trace back is different in the sense that you always keep the maximum score somewhere in your data structure, and you trace back from there as opposed to the bottom right. Most of the time people actually look for local alignments. In our case, we also look for local alignment because we don't know how this read aligns to contig. It might be in the end of the contig, it might be in the middle of the contig. So I'm just trying to find where it is. The global alignment wouldn't work. Okay, so I said there's different ways of getting parallelism out of this problem. And you can already think about trivial ways to get parallelism. I say trivial, but this is in practice working very well. The top left is the diagonal wavefront algorithm, very famous. If you think about each anti-diagonal that's shaded differently, all these entries are independent from each other. I can compute them independently. They only depend on the previous anti-diagonal, right? So just scan through this thing. Similarly, I can do column by column. It's kind of more tricky. It's not obvious how it's done, but I'm not going to talk more about it. And you can, morph this shape any way you like as long as the dependencies are satisfied. Lots of fancy research in parallel computing theory has gone to dynamic programming and satisfying its dependencies. In the end, what I call these kind of parallelizations are fine-grained parallelism, because for each little location in your dynamic programming table, a different thread is executing. It's pretty fine-grained. And one of the problems is how much parallelism is in there on the figure on the left, diagonal wavefront algorithm. How many threads can execute at the same time? You don't need to give me the exact number, on the order of, like I can only execute whatever the number of entries on that anti-diagonal, right? So which is more or less the sequence length. I mean, it's a little wider than that, but more or less the sequence length. So in fact, it's shorter than that at the beginning. So the problem there is if I'm aligning not so long sequences, there's not enough parallelism. Some of it will be burdened anyway, meaning that if you're aligning 100 base pairs to 100 base pairs, and you have 100 threads, it's a little naive to expect 100 times speed up, right? So some of that parallelism will be burdened because of the loop startup costs and so on. So you need kind of longer sequences for exposing enough parallelism, but these days we do have them, and the number of threads are not huge, so this is effectively used in a lot of multi-core implementations, still today. You can read a lot in a recent computing surveys. But I'm going to talk a little bit about an alternative for coarse-grained parallelism. And this is kind of go first off and tell you about how to run this dynamic programming algorithm, both Needleman-Wunsch global alignment and Smith-Waterman local alignment, without the m times n space. M times n complexity, I can't beat that if I want optimality. But do I really need to keep all of the table, the m times n size table, in memory? Or can I get away with smaller? So that is a question that bothered people for a long time. They came up with simple ideas that, for example, what the simple idea was doing is, your block rows. I was just computing a block of rows and recomputing it as I need it. But if you run the math, and I'm not going to do it now, it doesn't help. Your complexity, your space will go down to linear, but your complexity will go to m times n squared, because the sums don't go down geometrically. Instead, this is a really old idea by Hirschberg. You basically find the middle edge. Suppose you know the optimal alignment, and I'm not going to tell you how to find it. Suppose you know the optimal alignment. Now all you need to do is to cut it in the middle, right? So in this case, I'm going to say this creates two sub-problems that I only need to compute the top left and the bottom right sections. And I can recursively keep doing this. This is a cool idea. I still haven't told you, and I will actually not in this lecture, how you find that split. But you can find that split in mn time. It's actually expensive. Finding the optimal paths splitting location is as expensive as calculating it, but that's okay. Because the extra recursion will not have asymptotically more time. So the sum will still be mn. So here's what's happening. Mn is finding that split. Now the recursive calls are creating these n squared 2m costs. Sorry, n over 2 times m cost, n over 4 times m cost. And once you sum all of these costs and write them down, since this is geometrically going down, the nice thing is it sums up to m times n. This is different than doing block rows where the sum wasn't actually coming up right. So why did I talk to you about this? This is for parallelism, coarse-grained parallelism. I mean, it's kind of nice to be able to do this in linear time. But other than that, does this algorithm give you a good idea on how to exploit parallelism? It kind of does, right? If I can find the middle edge efficiently, all I need to do is to recurse. And that's exactly what's happening. And again, not going to go into too much detail. Hirschberg's recursion is exploited. The naive application of that recursion doesn't actually give you optimal parallel performance. You get a lot of terms that are not divided by p, so they become bottlenecks eventually. But an extension of those ideas, actually several extensions by several different authors, will eventually get you to an algorithm where it will use the optimal m times n over p space and m times n over p time. Unfortunately, these are sufficiently complicated that unless you have to implement them, knowing they're existing is probably enough for your purposes, unless you're going to invent a new algorithm. But this required like a subsequent number of papers. First, some of them managed to get the time optimal, but each processor was using more than linear space. Some of them got the linear space right, but the time was increasing. So this took several iterations of publications to come to an algorithm that extends Hirschberg's idea to an optimal parallel coarse-grained algorithm. But the general idea is the same. You find the splitter following the optimal path in the middle and recursively calls two sub-problems. 10 minutes. And the last topic. By the way, this is going to be the last lecture of any of the assigned lecturers. So the 3 more lectures, there will be one lecturer to introduce the guest lecturers all the time. because we don't want to disappear 3 lectures before the class and you'll never see us. And you can still ask questions to us in the beginning of those lectures about any pressing problems with projects and so on. So let's come to suffix arrays. This is very tricky. I wanted to talk about suffix arrays right after indexing with hash tables because they serve similar purposes. But I also wanted to talk about, it was right about time to talk about sequence alignment because we were talking about scaffolding. So know that the hash tables is not the only game in town. The hash table we used to limit the number of comparisons and say that read I is aligning to contig or read I is aligning to read J. There's another game in town, it's called suffix arrays. I can construct, instead of constructing a hash table, I can construct a suffix array and create the same result. Why would I do this instead of the hash table? This is more flexible. I can compare 2 genomes by just creating a suffix array of genome A, some spatial character in the middle, genome B, construct a suffix array, it will tell me all the parts that the genomes are aligning. Or I can find the longest common repeat sequences between 2 sequences. And in general, suffix array essentially indexes an arbitrary length substring. And you'll see what I mean. Hash table, you decide it's 3, and then you create a hash table, each entry is a 3mer. And you decide it's 4, it's a 4mer. So you have to know your error profile, you have to know the size of your genome to choose that index size. A suffix array is always a suffix array. You don't have a parameter for this. The picture is much better. Let's say you have Mississippi, the best example for this, for some reason. Well, a suffix array is really a sorted set of suffixes. So Mississippi itself is a suffix of itself. So that's indexed with 1, you can see here. And then drop M, Mississippi is over there. And the reason these are ordered this way is because of the suffix array construction. All that's happening is they're lexicographically sorted. It looks like magic, but there's nothing really. All I did is created all possible suffixes of this for a string of length n. There's n suffixes, especially if you consider the last element. There's an empty one that's not in this picture. The empty string, the end of string character, sentinel. But then I just sorted them. I can construct a suffix array, therefore, by using string sorting. Unfortunately, sorting is n log n. Comparing 2 strings of length n, in the worst case is order n. If I dumbly used string sorting, I would get a time of n squared times log n, which is horrible. We can do much better, and we'll do much better. And if I wanted to search a string within this, I mean, if it exists in the data set, it'll be a suffix of it, right? It has to be. At least it will be the prefix of a suffix of it. It doesn't need to be a suffix of it, but it will be a prefix of one of its suffix, and I can just locate it. I'll do a binary search. This basically is left, middle, right on a binary search. I'm not going to execute it, but it will tell me, okay, Issa, where can Issa be? Well, Issa is smaller than P. I is smaller than P, then I'm going to recurse that way. And eventually we'll find exactly where Issa should start. So you do binary search in this case. It's not exactly great, but you can get away without doing it either. If you augment this suffix array with an additional data structure, you can get away without doing the binary search. Suffix arrays are conceptually hard to visualize. And for that reason, before they existed, there was something called a suffix tree. That is really a tree structure of how this is formed. But they're very inefficient in terms of memory. They're 5 times more memory storage than suffix arrays due to all the pointers that is keeping. And they're inefficient to traverse because you follow pointers. So suffix arrays in practice is the only game in town. But some people like to think in trees because it's easier to come up with theorems. So in the last 7 minutes, I'm going to give you a sketch of this amazing idea. One of the 3 amazing ideas that occurred all in the same year, 2003, is how to construct a suffix array in linear time. Like not n squared, not n log n, linear time. So this is the easiest algorithm. And don't ask me why the algorithm is the way it is, because it's easier. There are algorithms which are more natural, but their analysis is so much more complicated. So what do? I divide the main idea is I divide my set into 3. All the suffixes that start at 0, 3, 6, 9, meaning that all the suffixes that start at the 0th location modulo 3, and all the suffixes that start in the first location modulo 3, and all the suffixes that start in the second location modulo 3. So I'm going to call each one of them is SA0, SA1, and SA2, like the ones that are starting in modulo 0, 1, and 2. And let's say I created this, and now I'm just going to look at the SA1, 2, meaning that all the suffixes that start in locations 1 or 2 modulo 3, not 0. So what happened is Mississippi itself is not there because it's starting in location 0, right? But the next 2 suffixes are in this data. The third suffix is not there because it's starting in modulo 3, right? So, okay. So I'm just going to compute this thing. Cool. And the main idea I'm going to use is I'm going to replace each 3mer, the sequences length 3, with their order. Suppose I sort this thing in linear time. I can sort things of length only 3 in linear time using radix sort. I'm going to sort them just like that, and then I'm going to name them with their order. I can do this in prefix sums or any other way I like. If it's serial, I can just go over them. If it's parallel, I can do prefix sums. So why is there 3 repeated? Because I can't resolve the order of the first and the fourth entries. They're both ISS, right? Okay, so if this was a distinct list, meaning this green list, lexicographical naming, were giving me distinct integers, I would be done. I would have suffix sorted the whole thing. But I'm not that lucky, usually. There's a lot of repeats in this data. So I'm not done, so what can I do? What I do is all the lexicographical names, meaning these new numbers I put for the suffixes that are 1 in modulo 3, that begin at first location in modulo 3, concatenate this with some special character that compares higher than everything else I have. And all the lexicographical names equal 2 in modulo 3, so I generate this guy. And what's going on is the first guy's location is 3, the fourth guy's location is 3, and then seventh guy's location is 2. That's where these numbers are coming from. The index of those guys, the lexicographical numbering of those guys in the original mod1 set and mod3 set. Now I'm going to recursively solve this problem. And due to lack of time, but the slides are there for you to compare it. Why is this working? You'll see that if 2 strings are, in relative some order, their lexicographical numbering preserves this order. So I don't need to compare the whole long string. If I just compare their lexicographical numberings that I just generated, that's equally correct. So that's that theorem on top of here. So I basically recursively converted my order n problem to an order 2n over 3 problem. And at some point, this has to stop. By construction, this at some point will create an lexicographical array of distinct entries. And then in this example, you're basically seeing what the benefit of this spatial end of string character and the concatenation character is. They just preserve the order correctly. How many minutes? I have almost no minutes. But it's actually almost done. So the nice thing about the skew algorithm, there are 2 more algorithms that are recursive that doesn't skew, meaning that they recurse in similar size data sets. The skew algorithm weirdly chooses 1 over 3 and 2 over 3 sets, right? But its analysis is simpler because now assume that the recursion successfully solved the order in SA1, 2, the big set that has size 2 over 3. Now, all I need to do to compute the order in SA0 is a very simple trick. I just look at the first character in each one of these suffixes. These are the suffixes that start in 0, 3, 6, and 9th location. Just look at the first character and the order I generated in the SA12 recursive call, right? Because what are they? They give me information about the next two items already, about how they are ordered. So I'm just going to reuse that information. So all I'm doing is sorting M concatenated by some integer that came from the recursive call I made so far. Beautiful. And then, so what did I get? I only got the order in SA0. So I have the correct order in SA0, I have the correct order in SA12. But I don't have the global order. And that merging is very simple too. The way I can merge these things is different from in the step that I just did before. I might have to look at not only just the one character, I might need to look at two characters, depending on what string I'm comparing it from. Simply because if I'm looking at comparing an entry from SA12, just looking at next element is okay. For SA0, I need to look at two more elements. But in the end, if I just put a triple or a pair, depending on the case, if I'm comparing, I mod 3 equals 1 case, I'm just gonna, my key to compare is a pair. If I'm doing a I mod 3 equals 2 case, I'm comparing triples. So, meaning that either this red case or the blue case happens. And then I'll be merging this with a simple scan pointer following case. I'm not going to go over. And then merge these two suffix arrays. These whole slides are very informative. It's better than most of the papers if you want to go over later. So what I'm saying is the merging can be done in linear time. Figuring out the order in SA0 from SA12 can be done in linear time, right? And for those reasons, my recursion is Tn equals 2n over 3 plus order n. And then it will resolve to linear time. That's all. And what happens in parallel is this picture. This is also the same authors that invented the skew algorithm, wrote the parallel stuff. Long, but let me show you what's going on. There are two parallel sorts, right? Because I did two parallel sorts, right? I did the sort to get the triples. First I extracted the triples in the beginning. And then I have to do now a sort with a complicated comparison function. Remember, I'm using this to get the SA0's sequence. I'm sorting the first character attached with the previous data I got from SA12. So there are two parallel sorts. There's a prefix sum for lexicographical naming to convert the triples to 1, 2, 3, 3, 4, whatever's. That can be done in prefix sums. The split of the data into three subsets, SA0, SA1, and SA2, is just data parallel. And nice thing is, since every third element is becoming one group, it is always balanced as long as the number of processors is more than 3. Right? Things will balance out. So it's data parallel. The whole communication is happening in those two sections where I need to do permutations. And that's basically the communication cost of this algorithm. But it's very simple to analyze. What you get is TC3 is parallel sort plus all-to-all plus some bottleneck that I have to do to bookkeeping. And it's the implementation defined. It needs to be at least log p. There's no way to get around the log p barrier in FP. The original implementation, DC3, was worse than log p, way worse, p square log p, something like that. But it can be improved. This is somewhat of a lower bound, right? And for these bounds to hold, of course, for this recursion to resolve to this result, these two things needs to be satisfied. The sort and the all-to-all both satisfy these constraints, so it's not that important. And you can find a reference over here. So we're already 3 minutes over time. I'll cut it short here. Thank you for your patience with the beginning of the lecture, with the projector problems, and thanks for your patience at the end of the lecture.